Let's go ahead and get started. Good morning, everybody. My name is Chris Modrich. I am the Valve Product Specialist for Lesman. I'd like to thank you all for making time in your busy schedules to join us this morning for the best practices for temperature regulators. In this session, Tim Gaynor, our Regional Sales Manager from Richards, which includes the brands of regulators and control valves of Jordan out of Cincinnati, Ohio, will cover how temperature regulators fit into a control loop, typical temperature regulator applications, advantages and limitations of temperature regulators, tips for sizing and selection, using temperature regulators for steam tracing, and then we'll do a little bit of Ask the Expert at the end. So Tim Gaynor has been in the industry for more than 26 years, and he's 23 years with Richards. And keep in mind that Richards is the parent company of Jordan, Bestebel, Low Flow, and Hex instrument valves that are all in the process valving space. So Tim's responsible for training and supporting the sales channel, and will come out and make sales calls with our salespeople, etc. So Tim, with all that said, you have the floor.
Beautiful. Appreciate it, Chris. And yeah, we'll talk about the topics that Chris mentioned. Trying to keep it light. I don't think this is going to be more than probably a half an hour. If we know everybody's busy, and we try to be respectful of your time and also appreciate your interest. So we'll go through pretty quick and do basics, and then at the end, as Chris mentioned at the end, we can ask some questions also. Without further ado, we'll hop into it.
So if anybody, Tim, hang on a second. If anybody does have any questions, you can use the question box, and I'll kind of pick a spot to interrupt Tim and throw them in as we go. So don't hesitate if you want to type, or it's not a huge crowd. So if you want to jump in and just take yourself off hold or off mute and ask a question, please have at it. Sorry, Tim.
Yeah, no problem. No problem at all. So here's a very wordy definition of what a temperature regulating valve is. A self-operated device in which the energy to position the valve closure member, in this case a plug or a seat, changes based on the temperature energy of the control variable. So what all those words typically, the most important part of this is they're mechanical devices that open and close, or if sized correctly and applied correctly, they'll modulate based on the temperature of whatever it is that you're controlling. It can be a cooling application, it can be a heating application, it can be a tank, heat exchanger, whatever it might be. But the main takeaway for definition is that it's a mechanical device for temperature control. And where do we see these applied? You know, as Chris said, we've been manufacturing these for over 50 years, and this is one of our legacy products as Jordan Valve. So we see these across a really broad industry: oil companies, refining companies, chemical manufacturers, anybody with a tank farm. You know, it's an inexpensive way to maintain tank temperatures, steel mills, pulp and paper plants, and non-critical temperature control applications. And what that means is if you have to have very precise temperature control, a mechanical means of doing that is not always going to be the best approach. And just trying to be honest with the people that are on here, you know, as Chris mentioned, we'll talk about limitations and we'll talk about advantages. And so if it's critical, then these usually aren't the best way to go. But tanks, larger heat exchangers, they can be great solutions for those. Some definitions real quick. Bellows is one type of actuator design, and I'm going to go into this a little bit more later in the presentation, but the bellows will have some type of fill that expands and contracts based on temperature, and that's one type of actuator that you see out there pretty consistently. The capillary is exactly as it sounds. That's the connection between the actuator and the bulb or whatever it is that's sensing the temperature, and we'll have the fill, whatever it is that expands, contracts, vaporizes, condenses to actually move the valve. The capillary connects both of those parts. Sensing bulb is what's actually touching, or in a thermal well, in whatever it is you're trying to control the temperature of it, be it a tank, again, heat exchanger. The sensing bulb is actually going to be in contact with the media that you're trying to control the temperature on. A span, and we'll talk a little bit more about this and do an example later, but the span is very critical. This is the amount of temperature change required to stroke the valve from full open to full close. So if your set point's 150 and you're heating, how cold does it need to get to open the valve all the way in order to get as much steam as possible through it? And again, that's a big part of it because the stroke length of the valve and the span are going to dictate the accuracy of the valve. And as I mentioned on a slide ago, that sizing is a big part of this because ensuring that you have the right CV will also help ensure that you have accurate temperature control. Thermal fill is the actual liquid in the thermal system that vaporizes and condenses to actually stroke the valve. And fills will vary based on temperature requirements. The thermal system is all of the components listed above. So the sensing bulb, the capillary, the actuator, all of that will have this thermal fill in it, and that is considered a thermal system. And then thermal well is just a fitting that goes into the tank or the heat exchanger, and then the actual bulb, sensing bulb, is placed in that so that if you need to change that or you need to do maintenance on the bulb, you don't have to drain whatever it is you're controlling the temperature of. So those are all very relative to these types of applications. So why would someone use a temperature regulator? There's a lot of different ways available to people and maintenance folks, engineers, to maintain, like in this case, tank temperature control. So in this example, we've got two different means of doing this. We want to keep a tank, heat exchanger, whatever, at 250 degrees F. Pretty straightforward. And so the top part shows what we see quite a lot of, a control loop in order to make this happen. So you've got an actual control valve, which is being operated with a 4 to 20 through an I to P, and you've got some type of controller, and there's going to be a temperature sensor in this tank that sends its signal back to this controller, which then tells the I to P, and the controller will send the signal to stroke the valves to either increase the amount of steam, decrease the amount of steam based on the temperature sensor. And this works well, but the main difference that you can see and figure out is the amount of cost that's involved. So if you have a fairly benign application, we're just keeping that tank at 250, and you can do it mechanically. Think of all the elements that you've now removed from the equation. You don't have to wire it to a controller, to a PLC or a DCS. You don't have to run shop air to it. You don't have to have an I to P that converts a 4 to 20 signal in order to make that happen. So that's one of the biggest advantages. It's just cost, and don't look at it just as material cost, because there's obviously labor costs involved with this when you're running conduit and wire and all that. So there's more to it than just the valve versus control valve and I to P and temperature sensors. So one of the realities of temperature control valves is they often won't have a great reputation. People will say, oh, they're sloppy, or they have poor reliability or poor performance or extremely slow reaction time. And depending on expectations, to be honest with everyone that's on here, those can be true. So for example, if you expect a mechanical valve to control within 1 degree plus or minus, you probably will find it to be sloppy, because it's very rare that they will control to that much accuracy. Extremely slow reaction time, again, that is a perception thing and can be accurate depending on expectations. But the reason that there is some lag, for lack of a better term, is you have this thermal fill. And for instance, let's say it's a heating application. Well, that fill needs to vaporize within the system and vaporize enough to actually close the valve. And that takes time. If you have a liquid and you're essentially boiling it, it takes time. It doesn't happen instantly. So again, depending on perception, slow reaction time can certainly be accurate. Part of applying these, again, is knowing, what's appropriate, how dynamic are the temperature changes or the flow rate changes through heat exchanger, for example. So those are all considerations. And sometimes they're not the right solution, but generally speaking, if it's not a dynamic application, they're great solutions for it. So span is essential, as I mentioned earlier, and I want to point out there's a typo at the bottom of this. So if you can see my cursor, that's supposed to be 175 degrees. So span is often related to the amount of stroke that the valve has. So as you can imagine, a liquid needs to vaporize to stroke the valve, or if it's a cooling application, vaporized liquid needs to condense, and that takes some time. But if the valve travel is pretty short, then it doesn't take a whole lot of vaporizing or condensing to actually have an impact on that. And that's where the span becomes a big deal. So in this example, real quick, we'll assume that one product has a 10-degree span. And that again means set at 150 I used earlier. Well, this example uses 180, so I apologize for that. But so the valve should be completely open to close between 175 and 185, 10-degree span. Another unit may have a 30-degree span. So in this example, you're going along at 100 GPM at 180 degrees F, and it's holding it there because the flow is pretty consistent. So it's pretty benign heating application. But then the flow rate increases and the valve needs to compensate for that. So we're going to increase the flow to 150 GPM. Well, with a 10-degree span, that's a 50% increase in flow. It's going to be basically 5 degrees change. So in this case, the drop in water temperature that you might see for a little while, again, it's supposed to be 175. Whereas with a 30-degree span, that 50% increase is now 15 degrees F, so it goes down to 165. So that may not seem like a lot, and maybe in a given application, it doesn't matter. Again, that's decisions for the client, for a process engineer, that's for them to make. But if you're trying to heat with this water for some reason, or it's a part of a bath where you have to maintain pretty consistent temperature, the difference between 165 and 175 could be significant. So span, again, usually linked to the stroke length of the valve for the most part, and then also a little bit to the fill fluid, which we'll talk about in a minute. So some things that a good temperature regulator should offer you, and you might have looked at the first picture and thought, well, that's a pretty simple device, and they are, but there's still some design features and attributes that should be available to anyone that applies these. For example, actuators that are easily replaceable. The actuator is usually part of the thermal system, so you want that to be replaceable easily. So ideally, the product can be replaced in line. You don't have to have any stroke adjustment, and that thermal system, inclusive of the actuator, is one part, for lack of a better term, so that you're not, you don't want to weld capillaries, you don't want to weld sensing bulbs, you don't want to do anything like that. So the actuator assembly should be very easy to replace. Maintenance free, same thing. The actuator, the thermal fill is the most critical part of these valves. If you lose fill or you don't have the right amount of fill, any brand, ours, anybody's, then they're not going to operate accurately or correctly. If you lose thermal fill, a lot of times they won't close or open when they're supposed to, period. So maintenance free, where you've got a one-piece system, for lack of a better word, is the ideal approach, where you minimize leakage and leak points. Sensitive control, so you want to react rapidly to minor temperatures. Again, short stroke is a big plus there. Over temperature protection, and this is a big one. and something to be careful about. So there's a lot of different fill ranges available based on your set point. And going back to that one example, if it's 180, what happens if something goes wrong in the system or with the steam supply or the thermal system, and the actual valve goes above that, the water that the bulb is in goes much higher. Well, a good temperature regulator will have over temperature protection, typically to 100 degrees, so that if, again, using the previous application, if that got up to 275, then you're still not going to damage the actuator or the assembly because of over temperature protection. So a good thing to watch for if you're ever specifying one of these. Offers numerous temperature ranges. So again, there's various fill fluids depending on the temperature you're looking for. If you use a fluid that can control between 50 and 200, it's going to be a lot harder to dial it in to the exact temperature that you want. So if you have more ranges available, maybe 50 to 80, 75 to 100, then the narrower range will help you dial in a little bit more accuracy. And again, when people have issues, especially perception issues with these, it's sloppy temperature control. So, if you pick the right range and it's narrower, then you've got a better chance of hitting your temperature target. Offer several CVs in a given line size. And this is big, anyone that has experience in any type of valve sizing and selection, be it mechanical pressure regulators, control valves, electrically actuated control valves, having the right CV is paramount to successfully applying the valve. And that's true with Mark 80 with temperature regulators. Having the right CV so that if it's a heating application, you get enough steam through the valve when it's open to maintain the heat. If you're oversized, you might allow too much steam through, or if it's a cooling application, you might let too much glycol through. So having several CVs in a given line size is very important. Several body materials, this is pretty straightforward, just so that you meet or exceed any facility specifications. And that comes up a lot with refining, a little bit in pulp and paper, the type of thing where you've got plant specs that you need to meet. So, more materials than just say like a cast iron should be available. And then offer different capillary lengths. So a lot of times where you want to measure the temperature in a tank is not real close to where the steam line is. So, if you have variable capillary lengths, that makes the actual installation easier. But again, if the point of reading temperature is, let's say, 30 feet away from where the actual steam source is, if you've got capillary lengths that go that far, then you don't have to repipe any steam lines. So again, installation is made a little bit easier through that means. So kind of going back to one of the slides we saw earlier, hopefully that makes sense. And if you're looking at keeping it 250F and you think about some of the little fundamentals we just talked about, then maybe you can get closer to where you're a plus or minus 2 or 3 degrees on an application like that, because you've got the right CV, you've got the right fill fluid, and you're measuring the temperature in the spot that you want to measure it. So all that's been direct applications where the sensing bulb is in the media that is measuring. But I wanted to talk about another application, which is steam tracing. Everybody knows what steam tracing is. So, a lot of facilities have exposed piping that needs steam tracing to protect lines, especially in the winter. And I'm just going to use water because it's so familiar and everybody gets that. So anytime the water gets below 32, there's a chance that your water lines are going to have issues. So a couple different ways to do this. You could install a manual valve on the steam tracing and assign a technician to operate it, which happens a lot. A couple of problems that can come up though. An unexpected condition may mean that the valve's not open. So you have a cold snap In October, it goes down to 28, but no one opened the steam valve, and now you've got lines freezing. Not good. Human error, technician forgets or misses, one of the steam trace valves. High cost, maybe there's overtime involved, that type of thing. Or to the contrary, they open it on that day in October when it goes down to 28, but then it goes back up to 70 2 days later, and it's just left open. So now you're just using steam and you don't need to. So there's a lot of, most of the things are tied to human error. And really, it's not because people are forgetful or anything like that, but everyone, operators, technicians, engineers, everybody's busy. And so one of the challenges that everyone faces is trying to keep up with all of the small tasks. And these aren't, weekly things that you're doing. So it's easier to forget these, easier to overlook these, but you can look at installing an ambient temperature regulator, and that measures exactly as it states, ambient temperature in the air around it. So it conserves energy, don't have to worry about the human error. You set it for, on the water application we're talking about, you set it for 38 degrees, and if it goes below that, it opens and lets steam into the steam tracing lines. That's what it looks like. So this one does not have a capillary. It doesn't have a sensing bulb or anything like that. So just the actuator is what senses the outside temperature and opens or closes the steam tracing line. And something like this will usually easily pay for itself in one winter season. Sometimes even in just the fall if you get some cold snaps in there, because you're not wasting energy at that point. So here's just a neat little diagram of how that might work, where you've got steam obviously coming in, and you've got your chemical, your oil, or we've been using water as the medium. And then once it drops down below, it lets some steam through. You've got your insulation, obviously a steam trap to get out any condensate. It's not the greatest example of how a steam trap should be piped, but we'll let that go as we're talking about temperature regulators. But here it is, taking care of that oil and making sure that, or excuse me, water, making sure that it doesn't freeze in your lines. Very, very straightforward. And then kind of a neat application where it uses both. So you've got a temperature regulator with the bulb actually in the oil, probably a thermal well, so you don't have to use, you don't have to drain the tank if you need to change anything, but you've got steam coming in there to keep that oil heated, and then also to an ambient temperature line, so that there's probably, again, water in here, or whatever it is you need to keep at a certain temperature, and that will open and do so based on the temperature outside. And there are three-way versions. These are usually hot oil applications where you're heating it, and if the oil drops below a certain temperature, it can divert the oil through a heat exchanger to heat it back up. So see that pretty often. And they're really, when I do see a three-way type temperature regulator specified for something, it's typically a hot oil application. So two actuator types are the most prevalent. One is bellows we talked about before, and bellows, it can be a stem seal type of product. In this case, it's the actuator, and the bellows will have a fill of some type that, again, condenses, expands, and that's what powers it. These usually have a longer stroke, and the bellows can fatigue over time. They are easily replaceable usually, and then the bellows type is usually a lower cost versus a welded sealed system. So this type doesn't have a bellows, just has a diaphragm internally, and the diaphragm is captured in between the two actuator plates, and it's welded closed. So it is a true sealed system, typically more reliable, and it's also easy to replace. But usually a little bit more costly because there's more material involved, and there's welding and things like that. So like so many things, it's probably going to be more reliable, so you're paying a little bit more for it. Common bulb types. So this is a standard bulb that just has a tank fitting, so it threads literally right into the tank. And then obviously you can thread a well in, as we've mentioned a few times, and then the bulb goes into the well. I'd say 95% of the time I see the standard bulb, it is threaded into a well, which is obviously the best piping practice, so you don't have to drain heat exchangers or tanks. I do see a fin bulb pretty frequently. This is more if you're doing temperature control of like a warehouse, where the fins will help pick up. They'll be a little bit more sensitive than just a regular bulb, and this will often be in the ductwork. So if you're heating a warehouse, this will be up at the top in the duct, and then it can let natural gas, if you've got a natural gas heater that is providing warm air through the duct. So I see that a lot, or sometimes in even in maintenance, larger maintenance shops where they've got this, and it just senses the temperature of the air as it goes through the ducts. And then just an extension type. So in some cases, companies don't want to measure the temperature right at the edge of the wall. So this is kind of a dead zone on this type of bulb, so that the actual temperature sensing part is further into the tank. So, you know, if you're just sometimes out at the wall, it's a little different than inside, and some people prefer to have the actual temperature inside. I think the last one is just kind of fun. So there's, speaking of bulb extensions, that is a 12-foot sensing bulb. So they really wanted the temperature to be read in the middle of the tank. And it's just something that'd be kind of fun to include a picture of. Something, it almost seems like it's ludicrous, but that's what a customer asked for, so that's what we did. But I just thought it'd be kind of fun to end with something a little unique. And that's it. Chris, did you have anything you wanted to add, or did anything pop up during this?
Something popped up. If anybody has any questions, you can just unmute yourself and jump in. Tim, can you go back to the slide where you show the you know, the wires with the controller and the whole bit, the two different loops? It was pretty early on. There you go, that one right there. So just to remind everybody here, the beauty of this is not only are you getting rid of all the parts and making this thing completely self-contained, but you're also getting rid of all the wiring. So if you're in a class 1 div 1 situation, a self-contained temperature regulator with a bulb and a capillary can be a much better value to install, and get very, very similar results, you know, assuming the valve is properly sized and installed.
Thank you, Chris. Appreciate it.
No problem. Okay, so we don't have any questions so far. Nobody's jumping in, so let me go ahead and wrap it up here. So, Tim, thanks for
that slide.
There you go. Okay. Thanks for your presentation. Appreciate it very much. For the attendees of today's webinar, if you have any specific application questions, feel free to give us a call at 800-9-LESMAN, L-E-S-M-A-N. If you don't know your account manager, feel free to ask for me, Chris Modrich. I'll make sure you get taken care of. If you'd like to drop me an email, I'm just Chris M, C-H-R-I-S-M at Lesman. If you'd like to know more about the technologies we supply, or our past webinars are posted both on our website at lesman.com and Lesman Instrument Company YouTube channel, which there's a bunch of stuff up. Surprisingly, you know, Tim and his coworkers and peers have helped us do multiple regulator webinars, and they have by far the most hits on our website, because it seems that wants to know more about mechanical regulators. They don't really get taught that in school. In general, if there's any topics you'd like us to cover, please don't hesitate to email me. We're always looking to do more webinars and add value for our customers. So at this point, if there's no further questions and none have popped up, we're going to conclude this. And thanks everybody for your time today.
Yeah, thank you very much. And as we said at the beginning, try to keep it to a half an hour. We want to respect your time, and thank you again for your interest. We appreciate it.
Yeah, thanks, Tim. Good job. Everybody have a wonderful day.
Cheers. Thank you.